I see you're back because you wanted to know more about complementary sequences. You thought Rayleigh's theorem wasn't enough for you. So here in this short video, we'll talk about how to find complementary sequences in a little bit more general fashion. So you might wonder, how often is it that we can find two complementary sequences in a formulaic fashion? Well, it turns out you can do this for almost every integer sequence, definitely if the integer sequence is increasing. And that's not just by taking the set complement, which you can always do, but we're going to do it in a formulaic fashion. So for our example, start with any increasing integer sequence. We'll start with the set of positive even integers, which are given by f of n equals 2n, and I've plotted them so that you can see them in blue dots. Now, given the integer sequence that you started with, you're going to compute a related integer sequence, which we'll call f down arrow of n. F down arrow basically counts the number of entries of your sequence less than a particular n. It's a little bit of a strange definition, but it makes more sense when you look at it visually. So we have our even integers. To compute f down arrow of 1, we draw a horizontal line at n equals 1, and we count the number of blue dots, or of outputs of f, below that red line. In this case, we can see there are no blue dots directly below that line. Likewise, there are no blue dots strictly below the dashed line at 2. But when we move the dashed line to n equals 3, we see there is one blue dot. And likewise for n equals 4, there's another blue dot, the same blue dot below it. For n equals 5, we have two blue dots strictly below the line. For n equals 6, we have two blue dots strictly below the line. And we keep going this way, each time moving the horizontal red line up one space and counting the number of blue dots below the red line. So that we see when n equals 12, there are 5 blue dots strictly below the dashed red line. Now, if you look closely at these two integer sequences, you will see that they are not complementary. However, we can take those two integer sequences and we just add n to both of them. So when we take our even integers and we add n, we get the sequence which is the multiples of 3. And likewise, when we take our constructed f down arrow sequence and we add n, we end up with the sequence 1, 2, 4, 5, 7, 8, 10. We get all of the numbers that are not multiples of 3. That is, all the numbers that are congruent to 1 or 2 modulo 3. And sure enough, now these two integer sequences are complementary. This is part of a theorem by Lambek-Moser, which states that if you start with any increasing integer sequence, then the two integer sequences that we constructed, that is f of n and adding n, and f down arrow of n, which counts the number of outputs of f less than a particular n, and add n to that, that will give a partition of the positive integers. If you're intrigued by this, you should try this yourself with an increasing sequence. You could try f of n equals n squared, or better yet, you can pick your favorite increasing integer sequence and go from there.